Okay.
Good morning. Let us describe primitive roots, which is the fifth module of analytic number theory. We know if 7 is an odd prime and 1 cube minus 1 is a multiple of 7, 2 cube that is 8 minus 1 is a multiple of 7. Similarly, we can see that 3 raised to 6 is also congruent to 1 mod 7 and 4 cube is 64. 64 minus 1, that is 4 cube is also congruent to 1 mod 7. But you can see 5 raised to 6 is congruent to 1 mod 7. You can verify. Also 6 square is 35. So 36 minus 1, it is also congruent to 1 mod 7. Therefore, among these numbers, say 1, 2, 3, 4, 5, 6, there is a least positive integer. For 2, we have 3, such that 2 raised to 3 is congruent to 1 mod 7, but 3 raised to 6 is congruent to 1 mod 7, etc. So, let us discuss what is the exponent. Exponent 7 of, we can say that 2, exponent 7 of 2 equal to 3. Similarly, we can see that exponent 7 of 3 equal to 6 and also equal to exponent 7 of 5. Similarly, we can see that exponent 7 of 4 is also 3. But exponent 7 of 4 equal to 3. Thus we can define exponent. That is, exponent of a number is the least positive number such that a raised to f is congruent to 1 modulo m. If m is any odd prime greater than 1, or then we can say that f is the exponent of a number if f is the least positive integer such that a raised to f is congruent to 1 modulo m. Then we denote as exponent m of a equal to f. So, exponent m of a equal to f if f is the least positive integer such that a raised to f is congruent to 1 mod m. But in this example, we see that exponent of 5 and exponent of 3 are 6. Exponent of 5 and exponent of 6 are exponent 7 of 3 equal to exponent 7 of 5 equal to 6. What is 6? 6 is 5 of 7. Therefore, we say that a is the primitive of m, primitive root of m, if the exponent m of a equal to 5 of m. So, in this example, we can see that there are 6 numbers corresponding to m equal to 7, but 3 and 5 have the exponent 5 of 7, that is 6. Therefore, 3 and 5 are the primitive roots of 7. The primitive roots of 7. That is the first definition. So, we define exponent and primitive root. The exponent becomes primitive root if if it satisfies the Euler's theorem. Euler's theorem, we know a raised to 5m is congruent to 1 modulo m. Here we see that so many numbers, say 2, 4 and 6 has divisors as the exponent. 2 has 3 as the exponent, 4 has also 3 as the exponent, but 6 has 2 as the exponent. All these exponents are divisors of phi m. Phi of m equal to 6. Here if m equal to 7. Yes. Then let us discuss some properties of this exponent. First property is important property is a raised to h is congruent to a raised to k modulo m if and only if h is congruent to k modulo f. If f is the exponent, exponent m of a, if f is the exponent m of a, then the first property states that if a raised to h is congruent to a raised to k modulo m, then h is congruent to k modulo f. The second property is, let us discuss later. Then, since a raised to h is congruent to a raised to k modulo m, we can write a raised to h minus k is congruent to 1 modulo m. So we assume that h minus k is a positive integer. Let it be h minus k equal to qf plus r, where r is a number such that 0 less than or equal to r less than or equal to less than f. But a raised to h minus k is congruent to 1 modulo m means a raised to qf plus r is congruent to a raised to h minus k. A raised to h minus k equal to a raised to qf plus r is congruent to 1 modulo m. That is, a raised to qf, a raised to f, the whole raised to q into a raised to r is congruent to 1 modulo m. But f is the exponent of a. Therefore, a raised to f equal to 1. So we get a raised to r is congruent to 1 modulo m. It is not possible because r is less than f. But we defined f is the least positive integer such that a raised to f is congruent to 1 modulo m. Therefore, the only one possibility is r equal to 0. Therefore, r equal to 0. Therefore, h minus k equal to q into f. Or h minus k is congruent to 0 modulo f. H minus k is a multiple of f. Yes. Or h is congruent to, so we get h is congruent to k modulo f. If we have the first property is, if a raised to h is congruent to a raised to k modulo m, then h is congruent to k modulo f, where f is the exponent m of a. That is the first property. By means of this property, we can see that if a raised to k is congruent to 1 modulo m, a raised to k is congruent to 1 modulo m means a raised to k is congruent to a raised to 0 modulo m. Then applying the above property, we know a k is congruent to 0 modulo f. K is congruent to 0 modulo f. But we know again, by Euler's-Fermat's theorem, we know a raised to phi m is congruent to 1 modulo m. Therefore, a raised to phi m is congruent to 1 modulo m. We can replace this k by phi m. We get phi m is congruent to 0 mod f, or we arrive a very important result, that is f divides phi m. F divides phi m if f is the, we see also for m equal to 7, we see that phi of 7 equal to 6, and all these exponents 2, 3, etc. divides phi m. 2 divides 6, 3 divides 6, etc. Okay. Then we have another important theorem, that is the property, that is a square, etc. a raised 1 a square a square, etc. a raised to phi m form are incongruent. For if not, let a raised to r is congruent to a raised to s, a raised to f minus 1, or a square, etc. a raised to f are incongruent. The third property is they are all incongruent. For if not, some of them are congruent, let a raised to r is congruent to a raised to s modulo f. That is a raised to r minus s. That is, yes, then we know modulo m. Then by the above theorem, we know r is congruent to s modulo f. That is, f divides r minus s. But we know the least positive integer is f, such that a raised to f is equal to 1. All these a raised to r and a raised to s are less than f. Therefore, r minus s is also less than f. Therefore, it is not possible. Therefore, our assumption is wrong. Therefore, all these are incongruent. A square, etc. a raised to f. Or we can say that a raised to f equal to 1. Therefore, otherwise we can say that 1 a square, etc. Either a square, etc. or 1 a square, etc. a raised to f minus 1 are incongruent. Then we can find the relationship between these primitive roots and quadratic residue. Reduce the residue first of all. The theorem states that if am equal to 1, then a is a primitive root, then a square, etc. a raised to phi m form a reduced residue system modulo m. We know, suppose a raised to I equal to a is congruent to a raised to j modulo m, then I is congruent to j modulo f, where f is the exponent m of a. Here we are given that a is the primitive root. That primitive root means exponent m of a equal to f equal to phi of m. Therefore, we get I is congruent to j mod f means phi m. That is phi m divides I minus j. Phi m divides I minus j. It is not possible. Why? We know these all numbers are less than phi m. Therefore, our assumption is wrong. Therefore, a square, etc. a raised to phi m form the reduced residue system modulo m. Conversely, if we assume that a square, etc. a raised to phi m are reduced residue system modulo m, then a is the primitive root. That is exponent m of a. M of a equal to primitive root means exponent m of a equal to phi of m. Since a square, etc. Let f equal to exponent m of a, we have to show that f equal to phi m. Since by Euler's-Fermat's theorem we know a raised to phi m is congruent to 1 modulo m. Also, a raised to f is congruent to 1 modulo. Therefore, we get a raised to f is congruent to a raised to m is congruent to a raised to m is congruent to a raised to 5m modulo m. A raised to f is congruent to a raised to 5m modulo m. But a square etc. a raised to 5m are reduced residue system. Therefore, f equal to only the condition is reduced system means a raised to f equal to f equal to only one condition is a square etc. are distinct. So we have seen that 5m equal to f. Therefore, we have a square etc. a raised to 5m for a reduced residue system if m is a primitive root. We see that for m equal to 7, we see that 3 is a primitive root. Then 3 square, 3 cube, 3 raised to 4, 3 raised to 5 and 3 raised to 6. 3 gives 3, 3 square is 9, 9 is modulo 7, it is 2. Then 3 cube is 2 into 3, that is 6. Then 3 raised to 4, 6 into 3, 18, that is 4. Then 3 into 5, 4 into 3, 12. 12 minus 7, that is 5. And 3 raised to 6, that is 5 into 3, that is 15. 15 minus, that is 1. Yes. Therefore, we get 1, 2, 3, 4, 5, 6. That is the numbers a square etc. a raised to 5m is nothing but it is the reduced residue system modulo m. So if a is a primitive root, similarly we can find 5 is also a primitive root of m, then 5 square etc. 5 raised to 5m form a reduced residue system modulo m. It is an important relationship between residue class and primitive roots. Yes. Then we are come on to the existence of primitive root modulo 2 raised to alpha. Primitive root modulo 2 raised to alpha for alpha greater than or equal to 2. We can prove that x raised to 5 of 2 raised to alpha by 2 is congruent to 1 modulo 2 raised to alpha. We can see that. That means if 2 raised to alpha is a primitive root. If a is a primitive root for 2 raised to alpha, we know a raised to 5 of 2 raised to alpha should be congruent to 1 mod 2 raised to alpha. This we know if a is a primitive root, then a raised to 5 of m is congruent to 1 modulo m. Here we can show that it is not possible. The only possibility is x raised to 5 of 2 raised to alpha by 2 is congruent to 1 mod 2 raised to alpha. That means 2 raised to alpha has no primitive root. If that primitive root exists, then a raised to 5 of 2 raised to alpha. Here we can show that 5 of 2 raised to alpha by 2 is congruent to 1 mod 2 raised to alpha. Let us examine. Suppose alpha equal to 3. If alpha equal to 3, 5 of 2 raised to alpha equal to 5 of, but 5 of 2 raised to alpha equal to, we know 5 of 2 raised to alpha equal to 2 raised to alpha into 1 minus 1 by 2. That is equal to 2 raised to alpha into 1 by 2. That is 2 raised to alpha minus 1. Therefore, 5 of 2 raised to 5 of 2 raised to alpha by 2 equal to 2 raised to alpha minus 1 by 2 equal to 2 raised to alpha minus 2. So to prove this theorem, to prove the non-existence of 2 raised to alpha, primitive roots of for 2 raised to alpha, it is enough to show that x raised to 2 raised to alpha minus 2 is not congruent to 1 modulo 2 raised to alpha. For that, put alpha equal to 3. When alpha equal to 3, we have alpha minus 2 equal to 1. Therefore, x raised to 2 raised to alpha minus 2 equal to x square is congruent to 1 modulo 2 raised to 3, that is 8. You can easily prove, because x square minus 1 equal to x minus 1 into x plus 1. But x is an integer, even integer, odd integer. So we can see that x is an odd integer. Then we have x minus 1 is a multiple of 2 and x plus 1 is a multiple of 4. Therefore, this x minus 1 into x plus 1 is a multiple of 8. That is, x square is congruent to 1 mod 8. That is, the theorem is true for alpha equal to 3. Then we assume that the theorem is true for alpha. Then we can show that is true for alpha plus 1 also. That is, we assume that x raised to 2 raised to alpha minus. But we know by Fermat's theorem we know, if 2 raised to alpha is a number, then x raised to phi of 2 raised to alpha is congruent to 1 mod 2 raised to. That is, but phi of 2 raised to alpha equal to 2 raised to alpha into 1 minus 1 by 2 equal to 2 raised to alpha minus 1. Therefore, by Fermat's theorem, we can see that x raised to 2 raised to alpha minus 1 is congruent to 1 mod 2 raised to alpha. If simply applying Fermat's theorem, then we can take square, that is x raised to 2 raised to alpha minus 1 equal to 1 plus t into 2 raised to alpha. Therefore, we get x raised to 2 raised to alpha minus 1 is equal to 1 plus t into 2 raised to alpha. We can squaring both sides. Squaring, we get here x raised to 2 raised to alpha. Here 2 equal to 1 plus t into 2 raised to alpha the whole square. That is equal to 1 plus 2 into t into 2 raised to alpha. 2 into t into 2 raised to alpha plus other terms containing 2 raised to alpha plus 1. That is, x raised to 2 raised to alpha is congruent to, is equal to 1 plus t into 2 raised to alpha plus 1 plus other terms. Therefore, x raised to 2 raised to alpha is congruent to 1 mod 2 raised to alpha plus 1. Hence, the theorem is satisfied. But is x raised to what is x raised to 2 raised to alpha? That is x raised to phi of x raised to 2 raised to alpha plus 1 by 2 is congruent to 1 mod 2 raised to alpha plus 1. So, if the theorem is true for alpha, it is also true for alpha plus 1 also. Therefore, for every alpha, x raised to phi of 2 raised to alpha by 2 is congruent to 1 mod 2 raised to. Therefore, there does not exist a primitive root if n is of the form 2 raised to alpha. We have 5 of 2 raised to alpha by 2. Then we can find a relationship between exponent m of a and exponent m of a raised to k. If a and m are relatively prime and d is the exponent m of a, d is the exponent m of a, then exponent m of a raised to k equal to d by d by kd, where kd is the GCD of k and d. We know since exponent m of a equal to d, d is the least positive integer such that a raised to d is congruent to 1 modulo a. Also, we assume that f is the exponent m of a raised to k. Exponent m of a raised to k. That means a raised to k, the whole raised to f is congruent to 1 mod m. So we get a raised to fk equal to 1 modulo m. A raised to fk is congruent to 1 modulo m. But f is the exponent. So we have the theorem that is shows that kf divides 0 mod is congruent to kf is congruent to 0 mod. By the first property we have kf is congruent to, that is a raised to kf is congruent to 1 mod m, and d is the exponent. D is the exponent of a, and a raised to kf, we know d is the least positive integer such that a raised to d is 1. Again we get a raised to kf is congruent to 1 mod m. Therefore, kf is a multiple of d, or d divides kf. Then we have d by kd also divides k by kd into f. But d by kd and k by kd are relatively prime since kd is the GCD of k and d. Therefore, it shows that by Euclid's lemma, d by kd divides f. D by kd divides f, or d by kd, f is a multiple of d by kd. But f being exponent means least positive. Therefore, f equal to d by kd, where d is the exponent of a and kd is the exponent of kd is the GCD of k and d. Then f is the exponent m of a raised to k. So we have a lemma, that is if d is the exponent of a and f is the exponent m of a raised to k, then exponent m of a raised to k equal to d by kd. Then we have a theorem that is if p is an odd prime, we have seen that, and d is any divisor of p minus 1, then every AD contains 5D elements where D is the exponent of A. If D is the exponent P of A, then every AD with the exponent D contains 5D elements. We have seen that for say p equal to 7, then p minus 1 equal to 6. Then we see that there are so many divisors. D is one of the divisor is say 3. Then it has exponent 4. M7 of 4 equal to 3. It has two elements. Exponent the elements having exponent 3 have two elements, 4 and 2. 2 and 4, there are two elements having exponent 3. That is the theorem states. If then, and it is 5 of 3. What is 5 of 3? 5 of 3 equal to 2. Therefore, every exponent D has 5D elements. That is the theorem. If P is a prime and D divides P minus 1 and exponent of A equal to D, then every AD contains 5D elements, where AD is the collection of all elements with exponent D. So AD is the set of all elements. We know by Euler's theorem, we know sigma D divides P minus 1, phi of D equal to P minus 1. We have already done in the second module. Again, let us define A of D is the set of those x lies between 1 and P minus 1 such that exponent M of x equal to D. Oh, we have already seen for M equal to 7, exponent A of say 3 contains 2 elements, 2 and 4. A of 1 contains only 1 element. A of 2 is another divisor. A of 2 contains only 1 element, 6. 6 square equal to 1. That is phi of 2 equal to 1. Phi of 1 is 1. Phi of 3 is 2. Also, what is phi of 6? Exponent with the 6. You see that there are only 2 elements, 3 and 5. That is phi of 6 is also 2. 1 and 5. So, AD is the set of those x element of x such that 1 less than x less than p minus 1 with the exponent m of x equal to d. So, for example, a of 3, a of 1, etc. Then, we have, these are all disjoint also. These all elements are disjoint. Also, each element contains FD, each AD contains FD elements. Therefore, sigma FD, D divides P minus 1, FD is also equal to P minus 1. So, from 1 and 2, we see that sigma D divides phi D is already by Euler's theorem, and also from this theorem we have seen that D divides P minus 1, FD equal to P minus 1. So, we get sigma D divides FD minus phi D equal to 0. Then for each case we can see that is also true, because we consider a raised to I for I equal to 1, 2, 3 etc. to D. We know this a raised to I has solution such that its solution it has a solution a square etc. a raised to I equal to. But by the above lemma, what is the exponent of this? Exponent of a raised to I equal to exponent p of a raised to I equal to d by k. Or simply a raised to I means I. But we can see that this equation x raised to d is congruent to 1 modulo p has only d solutions. They are a square etc. a raised to d. Here we get a raised to I, a raised to 2i etc. a raised to I into d. So we see there exist where the solutions are in some other order. So the number of solutions of this and a square, etc. are also the same. A raised to I, the solution of a is same. Therefore, exponent of a raised to id equal to d by id equal to d gives id equal to 1. That means this set of all belongs to AD contains the set of all elements such that ID equal to 1. That is the set of all elements X such that I and D are relatively prime. That is 5D. So AD, FD equal to the number of elements of AD equal to FD equal to 5. Hence the theorem. Thus, there exists a 1-1 correspondence between the solution of a raised to I and the solution a square, etc. a raised to d, but the exponent of a is d and exponent of a raised to I is d by id. But the solutions are x raised to d is congruent to 1 mod P has only d solutions. They are nothing but a square, etc. in some other order. Therefore, d by id equal to d, that is id equal to 1. Therefore, AD contains set of elements with id equal to 1, that is 5 of d elements. Therefore, the number of elements of AD is fd equal to 5. Therefore, fd equal to 5. Then we have come on to another theorem. So first we discuss primitive roots with reduced residual system. Then we are come on to primitive roots and quadratic residues in the fourth chapter. So we can state that G among the roots G, G square, G cube, etc. G raised to n is the primitive roots. So the theorem states that if G is a primitive root modulo P, if G is a primitive root modulo P, where P is an odd prime, then among G, G square, G cube, etc., G raised to n, G square, G raised to 4, etc., G raised to n are G raised to n r belongs to quadratic residue modulo P. Since G square, G raised to n, etc., G raised to P minus. Since G square, G cube, G raised to 4, etc., we know G square, G raised to 4, etc., G raised to P minus 1 are even numbers since P is an odd prime. Therefore, let G raised to n equal to, say, n equal to 2, n equal to even numbers, so n equal to 2. Therefore, G raised to n equal to G raised to 2m. Since G is a primitive root, G raised to n is congruent to 1 modulo P. That is, G raised to n is congruent to G raised to m the whole square modulo. So it can be written as G raised to m, which is an element of this quadratic residue, this primitive roots. G raised to m, the whole square is congruent to G raised to n modulo. We know if x square is congruent to n modulo P, then n belongs to the quadratic residue modulo P. Therefore, n r. Here we get G raised to m, the whole square is G raised to n modulo P. Therefore, we can say that G raised to n belongs to residue P, where what is n? N equal to 2n. That means G square, G raised to 4, etc., G raised to P minus 1 belongs to nRP. And also the remaining terms G, G cube, etc., G raised to P minus 2 are also belongs to n r bar P. Okay. Then we have a lemma, that is existence. Before discussing the existence of P raised to alpha, let us discuss a lemma. That lemma states that if g raised to p, if g is a primitive root, if g is a primitive root, g is a primitive root such that g raised to p minus 1 is not congruent to 1 mod p square, then g raised to phi of p raised to alpha minus 1 is not congruent to 1 mod p raised to alpha. That is the lemma. Lemma states that if g is a primitive root, then if g raised to p minus 1 is not congruent to 1 mod p square, then g raised to phi of p raised to alpha minus 1 is not congruent to 1 mod p raised to alpha. We know by Fermat's theorem, g raised to, if instead of n we assume that p raised to alpha minus 1, then g raised to phi of p raised to alpha minus 1 is congruent to 1 modulo p raised to alpha minus 1. Yes. Then that is g raised to phi of p raised to alpha minus 1 is equal to 1 plus k into p raised to alpha minus 1. Then taking p power just as the square, we have phi of g raised to phi of p raised to alpha minus 1 into p, that is g raised to phi of p raised to alpha is congruent to, is equal to 1 plus p into k into p raised to alpha minus 1 plus p square into p minus 1 by 2 into k into k square into etc. So we get g raised to phi of p raised to alpha. G raised to phi of p raised to alpha is equal to 1 plus p raised to alpha into k plus higher powers of p raised to alpha. Therefore, g raised to phi of p raised to alpha is congruent to 1 mod p raised to into p. So we said it is, yes, p raised to alpha plus etc. Mod p alpha plus 1 etc. K into. So we see that g raised to phi of p raised to alpha is not congruent to 1 mod p raised to alpha. It is 1 mod p raised to alpha plus 1. It is not mod p raised to alpha. Therefore, it is not congruent to 1 mod p raised to alpha. But for alpha equal to 2, we know g of, for alpha equal to 2, we know g of phi of p raised to phi of p raised to alpha, phi of p raised to alpha minus 2. Alpha equal to 2, we have alpha minus 1 equal to 1. Therefore, g raised to phi of p, that is g raised to p minus 1, is not congruent to 1 mod p square. So, for p square it is not satisfied. Then we have seen that phi of p raised to alpha is congruent to 1 mod p raised to alpha plus 1. Therefore, g raised to phi of p raised to alpha is not congruent to 1 mod phi of p raised to alpha is congruent, not congruent to 1 mod phi of p raised to alpha. Then we have come on to the theorem. The theorem states that if that is the non-existence of p raised to alpha. So the theorem states that let p be an odd prime and g is a primitive root such that g raised to p minus 1 is not congruent to 1 mod p square. Then the case is there is at least one primitive root g such that g satisfying this equation, then it has at least one primitive root modulo p raised to alpha. So for that, first of all, we can assume that first case is that is g is a primitive root. If g is a primitive root, then g raised to p minus 1 is not congruent to 1 modulo p square. For if not, the theorem is okay. We assume that it is not possible. We assume that g raised to p minus 1 is, we assume the contradiction. G raised to p minus 1 is congruent to 1 mod p square. G raised to p minus 1 is congruent to 1 mod p square. Then we assume that there exists another number, say g1, such that g1 raised to p minus 1 is not congruent to 1 mod p square. But g1 equal to g plus p. So g plus p the whole raised to p minus 1, that is equal to g raised to p minus 1 plus p minus 1 into g raised to p minus 2 yes, p minus 1 into g raised to p minus 1 into p plus etc. That is equal to g raised to p minus 1 plus p square g raised to p minus 2 minus p into g raised to p minus 2 etc. But we are given that, we are assumed that g raised to p minus 1 is congruent to 1 mod p square. Therefore, it is 1 mod p square. It is also mod p square. So, it is minus p into g raised to p minus 2. But we have seen that g raised to p minus 2 is not congruent to mod p square. That g raised it is a model of p. Therefore, our assumption is wrong. Therefore, this g1 raised to p minus 1 is also g1 raised to p minus 1 is also not congruent to 1 mod p square. So that is the second part. For the first part, let us assume that p is the primitive root. Let p is the primitive root of g is the primitive root of p, and we can show that this g is the primitive root for p raised to alpha also. For that, if we assume that g is the primitive root, let t is the exponent p of p raised to alpha. Exponent p raised exponent. Yes. Let g is the exponent. T is the exponent of. T is the exponent g modulo p raised to alpha. Then t is the Then we have g raised to t is congruent to 1 mod p raised to alpha, where t is the exponent of p raised to alpha of g. Then we have g raised to t is congruent to 1 mod p also. But we are given that g is the primitive root. We have to show that G is also a primitive root for P raised to alpha also. That is the theorem states. If G is the primitive root of P, then G is the primitive root for P raised to alpha. If G is the primitive root of P raised to alpha, we know the exponent of P raised to alpha of G equal to phi of P raised to alpha. Phi of P raised to alpha, or T equal to phi of P raised to alpha. But since G raised to T is 1 mod P and G is the primitive root, means G is the primitive root, means the exponent of G is phi P, the least divisor. Therefore, T divides phi P. That gives phi P equal to, say, T. But we know T is the exponent of P raised to alpha. Therefore, G raised to phi of P raised to alpha is congruent to 1 mod P raised to alpha by Euler's theorem, Euler's-Fermat's theorem. We have P raised to alpha and T. What about this? T is the least. Also G raised to T is congruent to 1 mod P raised to alpha. Here, T is the exponent. Exponent means least number. It is by Euler's theorem. But to prove the theorem, we have to show that the phi of P raised to alpha equal to T. For that, here it is the least number. So T divides phi of P raised to alpha. So T divides phi of P raised to alpha. That is, T into Q divides phi of P raised to alpha. Phi of P raised to alpha. Sorry. T divides phi of P raised to alpha. Also T equal to since T is the exponent of A, that means phi P is the exponent. So G raised to T gives phi P divides T, implies T equal to Q into phi P. Yes. Since T is the G is the primitive root, G is the primitive root, means T equal to exponent of that is equal to phi of P. So G raised to T is congruent to 1 mod M gives phi T is a multiple of phi P, or phi P divides T. Phi P divides T, that is T equal to Q into phi P. So T equal to Q into phi P. So Q into phi P divides phi of P raised to alpha. That is, Q into phi of P is P minus 1 divides phi of P raised to alpha is P raised to alpha into P minus 1 by P. That is, Q divides P raised to alpha minus 1. So we arrive at the position that Q divides P raised to alpha minus 1. But Q is a power of P, therefore Q divides P raised to alpha minus 1 gives Q is equal to, say, Q equal to P raised to beta, with beta is less than or equal to alpha minus 1. If beta equal to alpha minus 1, the theorem is completed. Therefore, if beta is less than alpha minus 1, we know beta is less than or equal to alpha minus 2. Therefore, t equal to p raised to beta into p minus 1 divides p raised to alpha minus 2 into p minus 1. That gives t divides p raised to alpha minus 2. Therefore, we have the exponent p divides, therefore, phi of p raised, that is phi of p raised to alpha minus 1 is a multiple of t. That is g raised to t is congruent to 1 mod p raised to alpha. Since t is the g, but we know g raised to t is congruent to 1 mod p raised to alpha, but t is a multiple of phi. Therefore, we get g raised to t means phi of p raised to alpha minus 1, p raised to alpha minus 1 into second is congruent to 1 mod p raised to alpha gives g raised to phi of p raised to alpha minus 1 is g raised to phi of p raised to alpha minus 1 is congruent to 1 mod p raised to alpha. It is not possible by the above lemma. Therefore, our assumption is wrong. Therefore, the only possibility is beta equal to alpha minus 1. Therefore, we get then phi of t equal to, therefore t equal to q into p minus 1 gives q equal to p raised to alpha minus 1 into p minus 1. Q equal to p raised to alpha minus 1 into p minus 1 equal to phi of p raised to alpha. Therefore, the t, the exponent of p raised to alpha equal to phi of p raised to alpha. Therefore, phi of p raised to alpha is a primitive root if g is a primitive root, provided g raised to p minus 1 is congruent to 1 mod, g raised to p minus 1 is not congruent to 1 mod p square. That is the theorem. If g is a primitive root, then p raised to alpha is also a primitive root if and only if g raised to p minus 1 is not congruent to 1 mod p square. Then let us examine the existence of then 2 mod 2 p raised to alpha. So, whether the exponent or primitive root of this primitive root for 2 p raised to alpha exists. If that exists, then exponent of 2 p raised to alpha of say g equal to phi of 2 p raised to alpha. If there exists a g such that exponent g of 2 p raised to alpha equal to phi of 2 p raised to alpha, then we can see that this 2 p raised to alpha is also a g is a primitive root for 2 p raised to alpha. Let us assume that f equal to, assume that f is the exponent of this 2 p raised to alpha. That means there exists a g such that g raised to f is congruent to 1 mod 2 p raised to alpha. That is g raised to f minus 1 is a multiple of 2 and multiple of p raised to alpha. That is g raised to f is congruent to 1 mod p raised to alpha. But we know. So exponent p raised to alpha divides g. Therefore, exponent of p raised to alpha of g. Exponent of p raised to alpha is a multiple of that is f divides, exponent of p raised to alpha divides this f is a multiple of this. Why? Exponent of that is the least number such that g raised to f is 1 mod p raised to alpha. Here we get g raised to f equal to 1 mod p raised to alpha. Therefore, f is a multiple of exponent p raised to alpha of g. That is but that is 5, but g is the primitive root for p raised to alpha, so it is exponent of that is 5 of p raised to alpha divides f. But we know 5 of 2 p raised to alpha is also equal to 5 of 2 into 5 of p raised to alpha, but 5 of 2 is 1, therefore it is equal to 5 of p raised to alpha. Therefore, we get 5 of 2 p raised to alpha divides f. Again, we can apply Euler's Fermat's theorem. That is, g raised to 5 of 2 into p raised to alpha is congruent to 1 mod 2 p raised to alpha. That is exponent of this. Exponent of 2 p raised to alpha is f. F divides this 5 of 2 p raised to alpha. So from 1 and 2, we see that 5 of 2 p raised to alpha equal to f. That is, this 2 p raised to alpha has an exponent. G is the exponent of 5. G is the exponent of 2 p raised to. Similarly, we can show that there is another theorem. That theorem is very simple. That is given for any m not of the form m equal to 1, 2, 4 p raised to alpha and 2 p raised to alpha. If m is any number of the form, not of the form 1, 2, 4 p raised to alpha, etc., we have seen that they have primitive roots. They have no primitive roots. So for any this m, we can easily show that just as the first case, that is a raised to 5m by 2 is congruent to 1 modulo m, where m is of the form m equal to not of the form this. So it may be 2 raised to alpha into p1 raised to alpha 1 into etc. p2 raised to pk raised to alpha. Okay. Thank you.